All right, everyone, welcome and thank you for being here today. My name is Patty Harburg Petrich, and I am the past president for SEOC. And today we have a really great presentation on building settlement and structural collapse analysis presented today by Dilip Khatri. Before we get started, I would like to thank our SEOC anchor sponsor, CSI. And I would also like to thank all of our sustaining sponsors. Thank you all for everything that you do for SEA. I'd also like to remind all the attendees about a few great events we have coming up. On October 18th, we have our OC membership breakfast meeting. We have SAP training on Saturday, October 21st. This is a great opportunity if you haven't done it before. And we have Structured Connections in the Inland Empire on October 25th. We'd love to see you all there. And with that, I'd like to introduce Dilip. You may all know Dilip from his work creating our Something from Nothing film series that we debuted this year. But Dilip has a lot of other capabilities and areas of expertise. Dilip is a structural engineer. He has over 40 years of experience, and he's a member of SEOC. Dilip is a faculty member at Cal Poly Pomona, and he holds credentials from 3 universities. Dilip has a PhD, 2 master's degrees, as well as his BS in civil engineering. And Dilip has presented a number of papers and technical guides over his career. With that, Dilip, I will turn it over to you. Thank you so much for being here today, and I can't wait to hear your presentation.
Thank you so much. Thank you to CEOSC for the invitation and the opportunity to present this paper. Thank you, Patty, and it's always a pleasure to be participating with the organization. I just want to say that SEOC has been an integral part of my career. I've been a member of SEOC for 41 years, and I've always gained a lot of good karma from SEOC, and I try to return the favor. So thank you very much. I'm pleased to be here today. Before we get started, first of all, are we all able to see the presentation there? Is that working okay on the screen? Okay, great. So first of all, I want to be clear that my role in today's presentation and what I'm presenting is strictly my own work. I'm not hired by any organization or government agency. This is for information only, based on experience over my career. I'm not providing any expert opinions or anything here to be derived for any legal cases. I'm not working for any property owners or law firms, and we're just providing, this is just for discussion only, and it's not intended for any legal use or anything outside of just a conversation. It's for information only. And so just to be clear that I'm not representing any, I'm not working for any university or research organization, and this hasn't been funded by anybody. This is all my own work of my own efforts, and just to be clear on that. So just a quick overview, we have a very large inventory of buildings in this country, 344 billion square feet of space, commercial and residential, out of which residential covers the majority of it, commercial about 87 billion square feet. And if we break down the entire infrastructure of buildings in this country, we have 4 basic materials: steel, concrete, masonry, and wood. 75% of our inventory is built from wood, 25% with the rest of it, steel, masonry, and concrete. So the focus of my talk today is to discuss something that's really not taught to us in school. It hasn't been really researched, and that is the impact of soil movement or earth movement on buildings, on foundations, and on structural performance. Now, we all know that we deal with settlement issues and we analyze for the settlement of piles and foundations, but what effect does it have when those settlements exceed the tolerable limits? And what are the tolerable limits? That's also part of the conversation today. From an insurance standpoint, it's a very big deal because soil movement, earth movement, as it's called in insurance policies, is normally not covered. It could be covered under a legal case if it's a patent or latent defect. Those are legal terms which deal with time limits. I won't get into the legalities of that, but those of you that have done expert witness work, You have the patent and latent defect time limits, which are 4 years and 10 years in California. Could be covered as a design defect, could be covered as a construction defect, or perhaps even negligence. But once you get outside of the 10-year statute of limitations, which is, I believe, the latent defect coverage, you are basically not covered. The building owner is not covered for anything that happens from soil settlement. So this is a very big deal. I think it's a very big deal, and it goes under the radar of a lot of our studies. And before I get into the technical aspects, I just want to point out a few collapses that have occurred recently, which we're all aware of. There's the Surfside collapse, and I'm not making any assertions or claims here that was related to settlement, because the cause is still outstanding. We don't know. They haven't issued the final report yet from the National Science Organization. I forgot the name of those guys. Anyway, but look at the impact: 160 people, or I think it's now that was revised downward to 105 people. There's definitely water issues. Is there sinking of the building, soil subsidence? NIST, there it is. NIST hasn't issued their final report. We do know that the structural engineer gave warning letters to the HOA 3 years before the collapse. We do know that. But, so this is a pending, very, very big pending case here that's still open-ended. We haven't come up with any conclusions, and I doubt there'll be one definitive cause, but it's an open file where settlement possibly could have played a role. And just to look back on history, just to let you know that these things have been going on for quite some time, I wanted to point out, so that this happens on large projects, major projects. There's the Kansai Airport in Osaka, Japan, built by the Japanese, which originally was planned to be $8 billion, has turned into $20 billion. And it's basically a reclaimed land using 26 million cubic yards of fill. And it's been sinking. It's been sinking for the last 30 years. It was estimated to sink to 13 feet. It's now sunk over 38 feet. And they just keep filling up the runways in order to raise the runway elevations. So in my estimation, even though that may be a functioning airport, that to me is a fail. Because these are the kind of things that, if it was, engineers are supposed to prevent this from happening. So these things do happen on a large scale. Coming closer to home, we just had the parking structure collapse in New York City. 57 Ann Street parking garage, built in 1925, had a lot of violations. And this has sparked a whole review of all the parking structures in the city of New York. City of New York has issued a mandatory requirement to have all their parking structures analyzed, which I think that should be expanded to include all buildings, because why just parking structures? All of their buildings should be examined. But this collapse, again, the cause is unknown. And it was a sudden collapse, and as you can see, quite fatal. 1 person dead, 5 injured. Could be much worse. But New York City has a lot of old buildings. And then we have the bridge collapse in Pittsburgh, which again, we don't know the cause. It's still under investigation. This bridge was scheduled for a speech by President Biden on that very date to discuss infrastructure, and the bridge collapsed in the morning. So my point here, and I could go on, there's in Southern California, we've had the collapse in near Portuguese Bend in I forgot the name of the location. Sorry, my mind just went blank. Anyway, the houses that slid down the landslide down there in Rancho PV. And that was, again, a sudden collapse. So we as an association, I think as an organization, should be actively involved in these investigations, and we really should be asking a lot of questions. Of course, we have to wait for authorities to do their analysis, but I know that as structural engineers, we're very actively involved in analyzing when earthquakes occur, and we should be taking this just as seriously. So let's get into the technical aspects. So going back to school, we have been taught as structural engineers, in my figure here, that all supports fixed and the ground does not move. A, B, and C stay level. That's the way we've analyzed everything since college. That's the way all of our exams are taught. That's the way our practice is run. Our industry is based on A, B, and C being level. And I'm here to tell you that they're not. Okay, so the first reality check is the ground does move. So the real situation, the reality is that A, B, and C are really 6 degrees of freedom springs. They have 3 translational spring stiffnesses in 3 different directions and 3 rotational spring stiffnesses. So there are 6 degrees of freedom at each base. And if we were to analyze every structure like that, it would be very, very complicated. So I'm not attempting to do that today. I'm only pointing out that this is a topic that has received very little or perhaps zero attention. I've done quite a bit of research, literature search on this. And of course, I've been teaching the subject my whole life. There's nothing really out there. There are no papers out there that really analyze what happens when one point goes down because the spring stiffness degrades. And we're going to talk about that today in a very, very simplified way, because I don't have the research funds or the time. I'm a working, practicing engineer just like all of you. To analyze this for all of these effects gets very complicated very quickly. So to do a simplified, just to make the point of my talk, which is what happens when you have degrading spring stiffness on one foundation element, we take a look at a very basic, the first thing that we studied in structural analysis after the simple beam, which was the portal frame. And we have the portal frame here. And in my analysis work, I actually did do analysis with 3 degrees of freedom. I looked at this portal frame with a lateral spring stiffness, a torsional spring stiffness, and the vertical. I'm saving you that analysis because I found that the vertical spring stiffness was the one that was the most sensitive. So I didn't present the other 2, but they do affect the structure for sure. So we take a portal frame and we put a vertical spring at point B, which we will start with a very high stiffness value, not quite infinity, but a very high number. You can pick any number, 1,000,000 kip per inch, whatever you want to start with, which basically represents a fixed stiffness. And then we reduce that stiffness incrementally, and we see what happens to the structure. So you have your textbook analysis with the fixed base, which will give you a symmetrical moment diagram and a symmetrical shear diagram. I don't need to show you that. You all know that. You start with that, and then you degrade the stiffness. And this figure is a little bit incorrect because this node actually remains where it is in vertical alignment. It doesn't slide off to the right. It stays vertical. This, though, does slide to the right. You'll see that in the analysis. So what I did was I took a portal frame, and in order to avoid any legal issues, I'm not telling you from what building it is. I'll just say that it's from a building that recently collapsed. Okay, I'll leave it at that. And I pulled the drawings and the load. So this portal frame that you see here has the properties from an actual set of drawings from a building that actually collapsed. And it's simulating several stories up above. I won't tell you how many stories, but you get the idea. So we take this simple portal frame. We have 3 degrees of freedom on the right side. And as I said, I analyzed it for each independent degree of freedom degrading separately. In other words, holding 2 degrees of freedom fixed and then degrading the torsional spring, and then vice versa, holding the torsional spring constant, then holding the vertical spring constant, then degrading the lateral spring. I analyzed all 3 of them on this portal frame. I'm not presenting the other 2 results, although they did have an impact, but I am presenting the results of the one that had the greatest impact, which was the vertical spring, because that was the one that I thought was the most pronounced, although the others 2 did also have. That had the highest sensitivity rating. So the analysis, even though the spring may be linear, which in reality it may not be linear, in this case I'm treating it as being linear, and obviously in real soil conditions it could be highly nonlinear. depending on what the soil profile is. So this is, again, a simplification for the purposes of just this very simplified analysis. I'm holding the torsional spring and the lateral spring fixed, and I'm degrading the vertical spring. And there is a way that you could come up with a closed form solution on this. I just didn't have that time to do it. So I only did it, using RISA. RISA, I thought, was a really easy program to do this on. And all I did was I took that vertical spring and I dropped it 10%, 20. And at some point, I started to get a deflection. And it was the deflection that I was most interested in because, and I'll just stop for a second to make my point here. If you remember from school, when we did those tension tests in your structural lab, right? And you were pulling on the tensile steel. And in the same thing we could say for concrete, when you were doing the compression tests on the concrete, you can't really tell visually what the stress is in a steel member. I mean, you can't. By looking at it, you can't. Concrete, you might be able to tell only after it starts to crack, but you can't tell visually what the stress level is. It's really not possible. But you can definitely measure the deflection, and that will give you a method to measure the stress. Strains are measurable. Stresses are very difficult to measure unless you put a stress gauge on it. But even a stress gauge is really a strain gauge. It takes the strain and then it calculates the stress. So strains, which are deflections, are our, they're our signal. They're the yellow light that comes up before the red light. Every structure, before it fails, is going to experience large strains. I mean, of course, unless it's a sudden collapse, like from an explosion or an earthquake. But slow-level movements, long-term movements, will show themselves in the way of strains. So when I do a structural examination on a building, I am paying attention, looking for deflection, abnormal deflection, and cracking. If it's concrete, I'm looking for cracking. And to illustrate the point, we go back to an even simpler analysis, which would be the simple beam, where we are taught in school that the simple beam, point A and point B, are stationary. And if we relax the stiffness on one side, this will clearly change the moment diagram. It will change the moment diagram if we make it a cantilever beam, same principle. And the stress is going to go to the columns which still have a stable stiffness. This is a fact of physics and of the basic structural performance. So now, before I give you the results of the portal frame, I want to now extend this analysis to a multi-story high-rise, mid-rise or high-rise, whatever you're working on. And I'm primarily focused on frames right now, but the same principle would apply for all other structural systems, shear walls, coupled walls, moment frame systems, the whole gamut. And it would apply to all structures, wood, masonry. The same principle still applies. So now if you take a multi-frame analysis, and now if you have variable deflections occurring on the base, which is very possible, I've done quite a few structural studies where I have witnessed that and measured it. Now you can only imagine the complexity of this analysis and what's happening in the frame. Very complicated, very complicated. To figure out what's happening in the moments and stress, but I can say for certain, just taking that simple portal frame analysis, that when you apply it to a multi-frame analysis, things get very complicated very fast. And you will have magnified moments or amplified moments in joints that were not designed for them. So this is the real world, uneven ground settlement. Let's go back to our basic case. So in our basic case, in our practical analysis, I've taken my structure, I've modeled it, and I am reducing the stiffness on one side. All these dimensions are from an actual frame, portal frame, from an actual multi-story structure. And I did the two cases, the case A, which is the fixed space model, which I don't need to present. That's going to have symmetrical moment diagram, symmetrical shear diagram. You already know the answer to this one. This is the one we're interested, where we're now changing the stiffness. And what do we get? So this is just a snapshot of the analysis using RISA, where we had vertical deflections on one side, which were on the level of approximately a little bit over an inch. Okay. And it's node 3 that's the one that's sinking, which obviously will affect node 4. Node 1 is stable. And what happens is, as you can see here, the structure leans to the right. I didn't plot the deformed frame on this because it was a little too much information. But what happens is you can see the moments are redistributing to the stronger joint. And so this column now, I didn't write down the original moment on here, but these moments are increasing just with a 1 1/4 inch deflection, are increasing on an order of magnitude of about 30%. So you have evidence here where the stress transfer to the good column is increasing substantially. A 30% increase in stress is a big increase. Your moment diagram is shifting clearly. And as this continues to degrade, this moment is going to get higher. And since this is just a simple 1 bay portal frame, these loads are real loads. You have 600,000 pounds of force coming in on this column. As this continues to degrade in a multi-frame, you can imagine that the load will get shifted to the other columns. But if you have multiple columns that are sinking, obviously those moments will shift to the columns that are not sinking. And when I talk about sinking, I'm talking about relative sinking. If the whole building sinks uniformly, in theory, nothing would happen, right? I don't think so, because there's no such thing as having a uniform settlement. You're going to have differential settlement. So what's the point? The point is that when we go look at structures, we should be paying attention to what's happening on the ground. We should be paying a lot of attention to what's happening clearly at these joints. We should be paying attention to deflection, deflection, deflection. So I do quite a few subterranean parking structures in my work. I look at a lot of them. I've done dozens of them, maybe hundreds. I don't know, I've stopped counting. But I'll show you some pictures of what this looks like in the field. But there are no guidelines in our profession. There are no papers that I'm aware of. If there are, please share them with me. There are no guidelines. There's no sort of handbook for us to go to. And there's nothing in the code about any of this. Now, we're talking about some of these buildings are 40, 50, 60 years old. And we may turn around and say to ourselves, well, that's not our problem. It's going to sink. Why do I care? Well, that's true, perhaps. But if you're hired by a client, residential client with homeowner association units, or you're hired by a commercial property owner to do a structural evaluation, then you got to worry about this. Because if you're going to issue a report on a building and you're going to say that that building is safe for occupancy and you haven't looked at this, I think we're missing something as an industry. We should be looking at it. I definitely do look at it. And I'm only suggesting, and this is just a conversation-only presentation, I'm only offering the suggestion from my own experience to my colleagues in the audience that you should consider this in your review. We should consider this in our review. And certain projects, when we get to projects that are like the Millennium Tower, which is, a major $600 million project that had some, I think, serious design issues in it, that settlement in the Millennium Tower is potentially a big issue. Okay, I'm not going to say what the issue is because I don't want to offend anybody, because I know some people will get angry when I talk about that, so I'll stop there. But I'm only raising the question. I'm not making any definitive conclusions here. I'm not blaming anybody or saying anything. I want to be very careful in my choice of words. I'm only offering a technical explanation that I think is a viable explanation on a topic that has not really been addressed, and I think it should be addressed. So here's some real world examples. This is from my files. These are projects that I'm currently working on or looking at. So this is a column inside of I think it's a 3-story building. Look at the condition of this column, right? These people have been cited by building and safety in this jurisdiction. And it took them 2 years to hire a structural engineer. 2 years. It's been sitting like this for 2 years. We came out there, we looked at this structure, and we found that a lot of these columns are like this, not just this one column. This is the kind of stuff that makes me nervous. Because how do I know, is this a compressive failure or is this column sinking? I don't know. And you can't tell by looking at it. You've got to measure. And you look at some of the other columns in this building. Look at this. And this is the kind of stuff that's not good. And there's no seismic restraint on these slabs, these beams. So that's another issue, is that this could all fall apart. This was built back in the 80s. And look at the spalling that you have up here. So we did do an analysis on this building. We did measure deflections. We advised them to do a retrofit, a rather substantial retrofit, to fix this seismic connectivity issue and to wrap the columns the best that we could do, best we could recommend. Some of the columns we felt needed to be short. And the bill is coming in quite high. They don't have the money. Okay, I can't go any further than that. All I can say to them is, look, you've got a problem. You need to deal with the problem. I've done my job. Now, if you can come up with the money, I can help you, but I can't do anything beyond that. But due diligence and our service in our industry towards life safety is very important here. And so I bring it to my colleagues' attention, to your attention, to consider these facts, and to perhaps as an industry, we should collectively work together to come up with something to address these issues. So I think I'm way ahead of time. Am I? Okay, well, that's fine. So my conclusions that I'm concluding here that footings, foundation settlement is a potential cause of failure. We can't say for sure without having measured data. I am advising that structural monitoring is essential in some cases in your structural assessment. Column alignment is important because if a column is not vertical and it's leaning, oh my God, that's a big issue because it introduces P delta effects and all kinds of other problems that you know about. And slab deflection needs to be measured. I focused primarily on reinforced concrete in this talk, but it's the same thing for steel buildings, and I have steel building examples that I could share. I just wanted to keep this very simple. Wood frame buildings, again, going to Rancho Palos Verdes, where they had the landslide situation, obviously the same exact topic there applies. Even though those are single-story or two-story buildings, so-called light frame, the foundation displacement affects the structure. And we normally are not measuring these things, and I think we should be measuring them. So Patty, I think I beat my own schedule. So
Well, Dilip, thank you. That was fascinating. I really appreciate it. For all the audience members, I would encourage you to add any questions that you might have in the Q&A at the Q&A button at the bottom of the screen. But Dilip, before we get started, I do have a few questions for you. So I was pretty surprised when you shared in your study that the moment on that adjacent connection increased by 30%. And I was wondering if that was surprising to you as well, and if there were other surprises that you discovered through this piece of work.
So actually, I was not surprised. And the reason I was not surprised with the result, I kind of already knew that was going to happen. And the reason is, I mean, give you a very simple sort of, human example is that, forgive me for using this example, but if you're standing and you get shot in one leg, what happens to your body? How does your structure react? You're going to shift all your weight to the good leg. Because that's the leg that's got to carry you. And so the physics of the structure is pretty much the same flow. the load always goes to the member with the highest stiffness. This is a fact. In any structural analysis, the stronger columns take the higher load. So I was not surprised. I didn't know by quantitatively how much it would be. The part that did surprise me was that it only took an inch of deflection to create a 30% increase in the moment. That did surprise me, because from 0 to like a quarter of an inch, it was like no change, half an inch. It's not a linear transfer. In other words, going from 0 to 1¼ inches, it's not a straight line curve. It's an exponential curve. In other words, there's very little transfer early on, and then all of a sudden it hits this number, which is about an inch, and then boom, all the stress starts transferring over to that other column. That part did surprise me, sort of. But yes, it was kind of an eye-opening result.
Yeah, interesting. Okay, we have another question from Monty Schultz. How much differential settlement do you typically allow before that stress transfer would get out of hand?
So by rule of thumb, not rule of thumb, there is actually a document from the Army Corps of Engineers published back in the 60s, which gives us rules for maintaining tolerable deflections. And the rule is 1 inch over 500 inches of length. So it's 1 in 500, which is about 1 inch for every 40 feet. That's kind of the rule that is not really a rule, but it's kind of it is a written down rule. It was developed by the Army. But again, that's a great question. And that's actually the question that I'm asking to be investigated, because that rule is going to change. The physics is, okay, it's going to depend upon, obviously, the length of the portal frame. Because if you have larger dimension portal frames or bays, and you have longer spanning beams, the moments are going to be higher. So the stress transfer equation is going to be a higher transfer at a lower deflection. If I have a 30-foot bay and I get a half an inch of deflection on one column, I can assure you that the stress transfer on that other column is going to be substantial. So it's not going to be the same analysis that I did today. That has to be done on a case-by-case basis to determine that relationship.
Thank you, Dilip. Another question for you. Can you talk a little bit more about how this has changed the way that you approach projects? I understand you've been thinking about this for quite a while, and I'm just wondering how this recent work has changed the way that you're looking at your project.
So on all of my projects, we didn't just start doing this recently. I've been doing this. I have been implementing my own procedures for more than 15 years. So we have been looking at deflections for at least 15, maybe 20 years. So it hasn't really changed anything. It's just we've sharpened our understanding. The collapses that have occurred have obviously raised awareness. Let me shut the phone off. Sorry about that. So it has sharpened our understanding, where we're now very sensitive to the topic. What it has done is, when I present my proposal to do this evaluation to a building owner, their immediate reaction is, well, why are you the only one that's asking to do this? When I talked to 3 other structural engineers, they didn't ask to do this. They only want to look at one connection and be done with it. And then I have to explain myself, and I have to give, sort of a mini technical talk. And that's where, in other words, I see, and understandably, I see that there's not a lot of understanding on this topic out there, which I think is a very important topic. And so my mission is to share it with the industry. And maybe you guys agree with me, or maybe you don't. That's fine. But at least I think it should be looked at.
I agree. Very important topic.
Because there's nothing in the building code on it.
Yeah.
There's nothing in the building code. Well, if there's nothing in the building code, technically we're not required to look at it. I think that's a mistake.
Well, Dilip, thank you so much for bringing this to our attention. Are there any other questions from the audience?
That means they either
Well,
that means they either seriously disagree or they just are done.
well, you did do a great job explaining the issue, Dilip. Thank you again so much for sharing this with us. Oh, we do have another question from Monty. Can you talk a little bit, Dilip, about why the building code has ignored this?
Well, maybe it's because I'm not on a committee. Perhaps it's my fault. I should be on a committee. But why they have ignored it, again, we are an industry that we learn, we live and learn. We wait for an earthquake, and then an earthquake occurs, and then we learn more. I think my honest answer on that would be we're so focused on earthquake that we have to consider the long-term effects on structures, effective soil subsidence, water, landslide, that soil conditions will not remain the same through the life of the structure. We are assuming that when the structure was built in whatever year, which could be 1920, that the soil has remained the same. And that is just wrong because the soil conditions change. You have water, flooding, drainage issues, subsidence, you have consolidation. The soil 50, 60, 70 years later is not the same as it was originally, even if it's on bedrock. Even the bedrock could fracture. So I think that's a misgiving, and that's a misnomer. And we should have some written standards for this. I think so.
Yeah. Dilip, another question. This one is from Mark Lowe. Mark says there are threshold settlement values for liquefaction. Are these close for the static condition? And he's referring to ASCE 7 table 12.13-13.
Okay, I'm sorry. I was reading another question that popped up here, which was the abacus question. I guess this was written somewhere else.
Yeah, this is in the Q&A section. So we'll get to the abacus question
There it
next.
is. Okay, now I see it. And I just wanted to read it real quickly. So give me a second here.
Sure, yeah.
Okay, there are threshold settlement values for liquefaction. We are close to the static condition. So that I would say are not that's not the same issue. What we're talking about here is long-term differential settlement that occurs. It's not liquefaction, because liquefaction is an earthquake related effect. We're talking about long-term settlement that has occurred for whatever reasons. Pile slip, excessive water coming on site or from another neighbor's property. And the way I know about this is because I've done hundreds, if not thousands, of building investigations. So I've been watching this for more than 3 decades. And I've seen the actual effects. I have quite a database of building inventory that I've looked at where settlement has affected the structure in all kinds of dramatic ways. Nothing to do with earthquake, nothing to do with wind, just long-term use, and we're getting to the point now where survivability of building inventory becomes a big question, because we've got buildings now that are approaching over 100 years old. We've got lots of buildings, millions of them, that are over 50 years old. We've got residences that are 70 or 80 years old. And how good are these structures going to be lasting? Are they good for another 50 years? And what's their condition today? This has become a big issue now because we have inventory that is aging, and we don't really have a standard document to evaluate those buildings, aging buildings, for these considerations.
Yeah, thank you, Dilip. Let's go to Yufeng Dong's question about abacus. He says, you just mentioned the simulation. Is Teresa, have you conducted this analysis through abacus?
So yes, I'm familiar with abacus. I've used abacus on more advanced analysis. It's a very, very sophisticated nonlinear analysis program. And yeah, I mean, you can use abacus. The thing is that, okay, when you do the initial analysis, I prefer to do an initial linear analysis so I can have I'm old school. I like to have my fingers on the numbers. I like to see whether or not my program is actually producing results that make sense. And a linear analysis is something that I can check by hand. And then you could go to an advanced analysis like an abacus analysis and actually model the soil. You could model the soil, nonlinear. You can get into some very complex programs. The Abacus is only one of them. There's a bunch of other ones out there. And I'm a PhD person, so I understand how all of that is very interesting to do. But before we get into the highly complex, let's first make sure we can understand the simple. Let's get the simple one done first, and then we could dive into the more complicated analysis. And a complicated analysis would help us in refining our quantitative estimation of what those stress transfers are, the moment transfer. We would get a supposedly more accurate value, but we don't need to start with that. I like to start with the basic linear analysis. So I think RISA is a good software to do that with. I've been using RISA for more than 30 years. Not that I'm a salesperson for them or anything, I'm not. But I find that their program is very easy to implement. But the other software programs can be done too. But I think you still need to do the basic one first.
Thanks, Dilip. Okay. Another question. This one is from Mo Tajvidi. Mo says, thank you for the instructive talk. When we see the settlement in the footing causing the cracks, what remedial measures do you recommend to the owner?
So yes, we have had that situation, and we have formulated repair plans for numerous buildings, and the solutions are a variety. I'll just give you a few of them. One possibility is using of helical piles, which may or may not be used to jack up the building. That depends on the circumstances, but helical piles, we've used those. We've done underpinning, where we've retrofitted with grade beams and piles to go down to good material to solidify and prevent further displacement. There are other solutions which I'm not a big fan of, but I'll just mention them, but I'm not a big fan of them. There's pressure grouting, there's compaction grouting. These are more soil remediation measures. I'm not a big fan of them for various reasons, which we could save for another day. But structural retrofit sometimes becomes necessary. Sometimes, if the deflections are not too bad, meaning that they're under an inch or they're within tolerance, which you can't tell by looking. You have to do some analysis to determine what that tolerance level is. We may recommend to do nothing and just monitor the structure. And if it gets worse, because soils are funny, they're really funny. They're very hard to predict. So sometimes you may want to just sit back and watch and see what's going to happen in the next 5 years. In some cases, like we take Rancho Palos Verdes, if they had been analyzing those buildings and done the appropriate surveys, I believe that those were giving warning signs in advance. They would have been advised to do something about them. Not that they would have done anything, but at least they would have been advised. Like the sample that I showed you where the buildings are cracked really badly, the one that I showed you in my presentation, I've given them the full scope to repair. Now they're dealing with a money issue. And I understand that, but at least I think that I've done my job.
Well, thank you all again for being here today and joining us for this webinar. Dilip, thank you so much for presenting this. I learned a lot today. It was very, very interesting, and I hope we can continue the conversation on this very important topic.
Thank you. Thank you for inviting me.
Great. And with that, we will end the webinar. Hope everybody has a great rest of their day.
Thank you.